Hi, Anna.
Good morning, Professor.
We'll get started in a few minutes.
It's okay. Professor Richard,
Yes, Anna.
I
What's
have a
up?
question. I forget, and I know this is in the syllabus, but the final you need to take is optional, right? Just optional.
Could you repeat that, please, Anna? I'm sorry.
Is the final optional, right?
It depends. If you have more than 90% on all 4 tests, it's optional.
Okay, it just replaces for the test, right?
I'm sorry?
The final replace the
Yes,
bad
it
score you have
replaces
in
the
it.
lowest test grade. That's right. But if you get
Okay,
more than 90% on all 4 tests, you don't have to take it. If you get more
okay,
than 80%, you can not take it as well, but you'd end up with a B in the course.
okay, cool. Thank you.
It's not the average, though. It's 90% on all 4 tests. And what
Okay,
you're looking at there is the complete test grades.
okay, cool. Thank you.
Hello, Ashley.
Good morning, Dr. Musgrave.
Okay, so let's get a start here. And we're going to start on, well, I did do a bit of Module 8 last time, and I did go through the questions. I'm just going to go through those again, just to see if anybody has any questions, but I feel like I covered them to a fair degree at the end of the last Zoom session. But if anybody has any questions about these specific problems, we'll answer those. So what I'm talking about here is question 5, question 6, question 7, and question 8. I think I will go through them just briefly again. Make sure that what have we got here? Make sure this is on. Might lose the share for a second. Okay. So if we've got a problem like this one, where we're trying to find out the empirical formula, what we have is percentages of RE and S. And the way that I recommend setting these up is to do a kind of a table approach here, with the idea being that we want to find out how many grams we have, how many moles of each we have, and then we need to divide by the smallest. And then we need to multiply, possibly. And then we need to round. And what we're looking for here is a whole number mole ratio of RE to S, so that we can come up with a molecular form, an empirical formula that has just whole numbers. And you can see all the answers here are exactly that. They're whole numbers of RE and sulfur. So presently what we have are percentages, and these represent the number of grams we'd have if we had 100 grams. So we assume we have 100 grams, which means the percentages match for grams. And then we need to figure out the moles. Now the moles are going to be based upon what we see in the periodic table. So it's just going to be based on these atomic masses that are here. Remember, you can always zoom in on this with your Command plus or Control plus, depending on what system you're on. And if we're looking at RE, got to find RE here. Here we go, 186.207. So the number, what we would do there is we're looking for the number of moles of RE. So it'd be 79.5 grams of RE times 1 mole of RE over 186.207 grams of RE. And we get 0.427. Now, we're not too interested here in the number of significant figures, because in the end, we're just going to end up with whole numbers anyway. So don't be too concerned about that. We do the same thing for the sulfur. And again, I picked that up off the periodic table that we're given. And I get 0.639 moles of sulfur. So that goes over here as well. All right, I'll stop here for a second. Does anybody have any questions? Anybody have any questions? Okay. The next thing we want to do is divide both of these by the smallest of the two. The idea being that we want to get a whole number mole ratio here in the end. So what I will do is divide both of these by 0.427. And what I'll get is, of course, 1 here. And 0.639 divided by 0.427 is going to be 1.4, well, it's going to be 1.50 over here. So that's what I'm going to have for my mole ratio of RE to S so far. But the problem here is that those aren't whole numbers. So I need both of those to be whole numbers. And the only way I'm going to be able to do that is to look at this and say, well, that's 1.50. That 0.50 is pretty close to a half. So if I multiply this by 2, I have to multiply both of these by 2, I'll get 2 is to 3. So we'll end up with RE to S3 as being the answer there. So the hard part here is this part, is recognizing, well, what do I have to multiply this by? And in order to do that, I recommend being aware of the fraction conversions of certain decimals. And as long as we're aware of those, there's really, it's really not too, you can't really go too far wrong with it. So if you're looking at the decimal and that's all you're doing is looking at the decimal, you want to be able to determine what fraction it looks like. And if it's 0.50, it's obviously a half. So multiplying it by 2 would be a way that you could get rid of that fraction. If it's close to 0.33, you'd multiply by 3. If it's close to 0.66, again, you'd multiply by 3. If it's close to a quarter, 0.25 or 0.75, you'd multiply by 4. Does anybody have any questions about any of that? It's not really something you have to memorize because you could always put that into your calculator to determine that. Any questions? Okay.
No, that chart helps, like just writing it down. When I was doing my problems, it helps.
Okay. Yeah, but you know, it's not something you would have to, it's not really something you have to memorize though, actually, because you could always just put those fractions into your calculator to come up with those, with those decimal values.
Correct.
Okay, let's take a look at the next question. Now, this one is about an oxide. Now, an oxide is a compound with oxygen and some other compound. And I mean, that's the definition we learned when we talked about them in Module 5, we talked about oxides. So if we're told that we have a mass of oxide, an oxide is going to have the formula, in this case, MnXOY, and that's the oxide. Now, I'll tell you this, oxide does not equal oxygen by itself. And that's really important. I think a lot of the time people see this problem and they think, oh, 6.91 grams of oxide, oh, that must be oxygen. No, no, no. The oxide is the manganese and the oxygen combined together. So in order to obtain the mass of oxygen, the mass of O is going to be the mass of the oxide, we'll say MnXOY, minus the mass of manganese. So in this case, it would be 6.91 grams minus 4.00 grams, which would be 2.91 grams. So that's where we're going to get the oxygen from. So the same thing then can be done as we did previously, and we can just go ahead and do grams and moles, and we can divide by the smallest, possibly multiply, and then round. So we do exactly the same thing as we did previously. We'll start off though with 4.00 grams of manganese, 2.91 grams of oxygen. And manganese, make sure that you're looking at Mn and not Mg. That's a common mistake that I'll often see here. But Mn is over here, it's 54.94. So we'll do, I won't do the working for that, but 4 divided by 54.94, that's 0.0728. And for the oxygen, 2.91 divided by 16, 0.181. And we divide both of those by the smaller of the two. And here we would get 1 and then 2.49. That's close to 0.5. So if we multiply by 2, we'll end up with 2 and then 5 as our final answer there. So it'd be Mn205 would be the answer that we would put for that. Does anybody have any questions? Question 7 is going to be a percentage question. And if we're looking at the percentage of oxygen in this one, what we would do is, if you've got a pizza and you've got a piece of it, and the percentage of the piece you have is the piece divided by the whole. So it's the same kind of deal as what we have here. So we've got 9 times the mass of oxygen, which would be 16.00, divided by the molecular weight of the entire thing, AlNO3, 3 multiplied by 100%. And then we would pick out whatever result was going to be the closest to that. I won't do that anymore unless anybody's got any questions about it. Anybody got any questions about number 7? The other possibility is the possibility of getting, say, a hydrate and looking for the percentage of water. To do that, it would be 2 times the mass of water, molecular weight of H2O, divided by the molecular weight of CaSO4.2H2O. And the way we get that would be 1 Ca plus 1 sulfur plus 4 times oxygen plus 2 times H2O. Multiplied by 100%. So that's the other possibility for question 7, would be to get the percentage of water. Does anybody have any questions? Question 8 is looking for the true formula. And what we have is an empirical formula, CF, but we have a molecular weight of 124 grams per mole. So what we're effectively trying to do there is try and figure out, well, how many CF units are there in that molecular weight? Because we know that it's going to be a whole number of those units. It could be 1, it could be 2, it could be 3, it could be 4, but we need to figure out how many units of CF there are in that specific compound. See, an empirical formula is only a mole ratio. So C2F2, C3F3, C4F4 are still valid mole ratios that would fit CF, but we need to figure out which one it is that would match that molecular weight. I think the easiest way to do that is to find out what the empirical weight of CF is. And CF would weigh, I think, 31. The way I get 31 there is 12 plus 19, which just is the other atomic masses off the periodic table for those elements. So 12 plus 19 is 31. So what I can do here is I can take the molecular weight and divide it by the formula weight. Sorry, the empirical weight. Which is going to be 124 grams per mole divided by 31 grams per mole. And you can see that that's going to be 4. So there's 4 CF units, which means C4F4 would be the true formula, since we do have the molecular weight there. So that's the easiest way of doing it. The other way is to do it trial and error. Say, well, is it CF? 31, no. C2F2, that'd be 62. C3F3, that'd be 93. And then C4F4, that's 124. So that's the other way of doing it. Anybody got any questions about the true formula? Okay, so that's it for Module 8. Did anybody have any other Module 8 questions? Those usually aren't too bad. They don't usually give people that much trouble, except for those tables and the fractions. That sometimes gives people hassles. Okay. Well, let's look at, I'm going to focus on here the the questions. Does anybody have any questions about Module 9? I might exit out of here actually, and we'll go take a look at the assignment. Okay, did anybody have any questions about the Module 9 assignment? So what I'm going to encourage you to do when you're going through and doing the assignment and the other quizzes is to use this modified flowchart where QA is grams of A or liters of A at STP, and QB would be grams of B or liters of B at STP. So those are really the only things that we need to deal with here. And it's a matter of knowing where you're starting and where you're finishing. So for this case here, where we're starting with moles and we're finishing with moles, we can see that this is the only part of the flowchart we'd be dealing with. And it's, again, all about dimensional analysis. And for this one, we know that the mole ratios here are going to be all determined by what we're seeing in the reaction. So what we're seeing here is some relationship. If we were to do this on paper, for example, it'd be like this. It'd be 5.0 moles of H3PO4. We know that the bottom unit was moles of H3PO4. We know that what we're looking for is moles of CO2. And we're looking for a relationship between H3PO4 and CO2, and that's up here, 1 mole of H3PO4, 3 moles of CO2. So you'll notice that's the approach I like to take, is put the units in first and then put the numbers in next to those at the end once we figure out what the relationship between them is. And that's how we get that answer of 15 moles of CO2. And of course, when you're doing this, the number 1 will be 3 moles of CO2. Number 2 would be 1 mole of H3PO4. And then the rest of these are unused. So you have to put number 3 in for each of those. And that's how you would you'll end up completing the entire assignment that way. Does anybody have any questions so far about any of this? So if you had something like this where you're looking for the number of liters of CO2 and you were starting out with 3.0 moles of NaHCO3, then you would be starting here at the flowchart and going through to liters. So the way you'd set that up would be starting out with 3.0 mole NaHCO3 times, and then a line, and then another line. We know it's 2 steps because we have to go from moles of A to moles of B and then to liters of B at the end. So liters of B is what's going to be here. We'll have up here the moles, actually liters of, what are we looking for? Sorry. We're looking for liters of CO2, and that's going to be B. So we'll have, up the top here, we'll have moles of CO2. And what I want you to notice is that everything that lines up across the top here is everything that we want, and it matches what's here in the flowchart. So we'll have moles of NaHCO3, then there'll be moles of CO2, then in this case, liters of CO2 at the end, because that's what we want. And then we also know that whatever goes on the bottom has to match whatever's up here, so it cancels. So that's how we know what goes in there. Then we can look at the relationship between the moles, and we get that from the reaction here. And it looks like it's going to be 3 moles of CO2, 3 moles of NaHCO3. And then the liters be 22.414 liters of CO2 to 1 mole. And that's the relationship between those. And you can see there's a little conversion thing here that helps you with that. 1 mole is that. Sometimes a mistake I sometimes see here is people will say, well, shouldn't that be 3 moles of CO2 because it has to match there? No, the unit has to match, the number doesn't. But this number here has to equal this number. There has to be a relationship between them. So 1 mole of CO2 needs to equal 22.414 liters of CO2. And that's here in the conversion that you see in the question. So you don't have to memorize any of that. It's right there for you. Does anybody have any questions? Okay, I'll go on to something a little bit more difficult. Let's look at this one here. And what it's asking for is the liters of CO2 when 49.0 grams of H3PO4 reacts. So for this one, we're going to be starting out with 49.0 grams of H3PO4. And we'll end up with liters of CO2 at the end, in this case, 33.6 liters of CO2. We're actually given that. So if we look at the flow chart, we're going to be starting here, and then we'll go to moles, and then we'll go to moles of B, moles of A, then moles of B, then Q of B, or quantity of B, which will end up being the liters of CO2 at the end. So again, you'll notice everything will match here. So that'll be moles of H3PO4. This will be moles of CO2. And this will be liters of CO2 because that's what we want at the end. We know that this will be grams of H3PO4 to cancel. We know that this will be moles of H3PO4 to cancel. And this will be moles of CO2 to cancel. And it should be that easy to come up with the units. Then we've got to figure out, well, what relates these units? What makes them equal to each other? So it'd be 1 mole is equal to the molecular weight of H3PO4, which is given 98.00 grams. And then the relationship, moles of CO2, moles of H3PO4, we get that from the reaction. Here we go, 1 mole of H3PO4, 3 moles of CO2. And then the relationship here, 22.414 liters is 1 mole, and that should give us our answer. Does anybody have any questions? One thing I can tell you about putting that into a calculator, and you know, we've got the on-a-lot calculator here. Actually, no, that's in the quote. That's in the. We'll get to that when we get to the test, and I'll show you how you can enter that into the calculator. All right. Anybody have any questions? I'll leave that flow chart there. Let's take a look at percentage yield or theoretical yield here. So when we're given a theoretical yield problem, the idea is, or a percent yield problem, what we're trying to do is we're trying to figure out how much of a product we're expecting to get. So it's all about starting out with a reactant and then figuring out how much product we're supposed to get. So when you're looking at one of these problems, the key is to look at the two things that you have here and figure out, well, which one's a reactant and which one's a product. Well, in any reaction, whatever's on this side of the arrow is the reactant, and whatever's on this side of the arrow is the product, which kind of makes sense because reactants are things that are reacting and products are things that we're getting. So whenever you're dealing with a theoretical, you want a theoretical yield or a theoretical anything, it's always about the product. Now you'll notice that we are given a certain amount of product here. It says 350 grams. That's what we got. But the thing is that we were supposed to actually get more than that. Theoretically, we should have gotten much more than that, but we didn't. We have to figure out exactly how much we were supposed to get. So then it does become one of these problems like we're just doing up here. But the key is we need to start with whatever the reactant is to figure out how much product we're supposed to get. So we're going to start out with 692 grams of NaHCO3. And what we're interested in is figuring out how many grams of Na3PO4 we should have gotten. I'm telling you this right now, it's not going to be 350 grams. It's going to be something more than that. I'll stop there for a second. Does anybody have any questions? So the idea here is to go ahead and do the same thing as we were just doing. We're starting out with NaHCO3, 692 grams. And what we're looking for at the end is grams of Na3PO4. So when I'm filling this in, I know that's going to be moles of NaHCO3. I know that's going to be moles of Na3PO4. I'm just getting that from up here. See, grams, NaHCO3, moles of NaHCO3, moles of Na3PO4. And then we're looking for grams of Na3PO4. And down here, it's going to be, grams of NaHCO3 on the bottom to match. This will be moles of NaHCO3. And this will be moles of Na3PO4. And it really should be that easy every time. So 1 mole and the molecular weight of NaHCO3, 84.00. Moles of Na3PO3 to moles of NaHCO3, NH3PO4, that would be 1, and NaHCO3 is 3. And then the molecular weight, 163.94 to 1. And the answer comes out, I think, to be 450 grams of Na3PO4. So that's the amount of Na3PO4 we should have gotten, but you can see here that what we did actually get was 350 grams, not 450 grams. So that's what we would be looking for there, would be 450 grams of Na3PO4. So that would be the answer there. Does anybody have any questions about these kinds of problems? Now, you're not asked to do this here, but if you were asked for a percent yield, that's one more step. And the percent yield would be actual over theoretical multiplied by 100%. The actual is going to be 350 grams. That's what we actually got. The theoretical is what we should have gotten. And you're expecting something less than 100%. So that should help you as well. And I think that comes out to about, let me see, I think it's 76% or something. Let's see. 77.8% would be the answer there. So we got 77.8% of what we should have gotten, but we figured that out based on that. Now, you didn't have to do that for question 6. You only had to go as far as getting the theoretical yield. But in problems that you'll do on the test, you will be expected to come up with a percent yield as well. Does anybody have any questions? All right. Now, the other kind of problem that you'll need to deal with here is called a limiting reagent problem. And the reason it's called that is because we're dealing with two reagents or reactants. And we're trying to figure out, well, which one gets used up first. So if you look at the videos I have that describe how this is happening, I talk about it in terms of cheese sandwiches. And I say, you know, if you've got one slice of cheese and two slices of bread, how many cheese sandwiches can you make? And the thing is that, you know, if you have too much cheese or too much bread, something's going to get used up first. And that's what we're trying to figure out here. So I'd recommend that you take a look at the soft chalk for more information about that. I'm just really going to focus on the nuts and bolts of solving the problem here. So the idea, the way that we handle this to see, you know, which one gets used up first is to do this in terms of a mole ratio. So we come up with two numbers at the end and we compare them. And the one with the smallest mole ratio is going to be the limiting reagent. That is the one that gets used up first. Does anybody have any questions or need any more background on the limiting reagent problem? Again, I would look in the module 9 soft chalk to determine what's going on here if you need more deep background information about what's going on with the limiting reagent problems. Well, there's two factors that we take into account. We take into account, first of all, how many moles of NaHCO3 we're going to be dealing with, and then the mole ratio with reference to how many moles are actually in the reaction. So for something like this, the way we handle it is we take the 100.0 grams of NaHCO3, we figure out how many moles we're dealing with, so it's going to be 1 mole of NaHCO3 over the molecular weight of NaHCO3, which is going to be 84.01 grams. And then we do times 1 over the number of moles of NaHCO3, which is 3 moles. And that's in the reaction. Now, sometimes this 1 here confuses people. They say, well, 1 what? There's no unit next to it. What's the story with it? 1 what? Well, the 1 there is, it's more a way of using a division without using a division. Because if we want to divide something by 2, we can also multiply it by a half. We're going to get the same result. But the 1 there doesn't have any unit associated with it. We're just using it to say, well, we're doing it by times 1 over 3 moles, not rather than dividing by 3 moles. So times 1 over 3 moles, but the 1 doesn't have a unit on it. So that allows us to come up with a number, but this whole number here won't have a unit. So it'd be 100 divided by 84.01 divided by 3. And we get 0.397. 0.3968. And like I said, it doesn't have a unit because everything cancels. And that's our mole ratio that we're dealing with for NaHCO3. Anybody got any questions so far? That's not the end of the problem, but anybody got any questions so far? We treat the other one the same, 100.0 grams of H3PO4. And what we want to do is, again, figure out how many moles of H3PO4 we're dealing with, which will be 1 mole over the molecular weight, which is 98.00 grams. And again, we follow the same pattern, be times 1 over 1 mole of H3PO4. And the 1 mole is from the fact that if we look at the reaction, it's just a 1 here. So you can see we're taking into account 2 things, the number of moles we have and then the number of moles that are used in the reaction. And that will allow us again to come up with another figure, which can be compared. I get 1.020. So you can see here that if you compare those two mole ratios, the smaller one is the NaHCO3, which would make the NaHCO3 limiting. It would be the one that's used up first. Does anybody have any questions about those limiting reagent problems? Very briefly, I'll just do something here to clarify things, just in case you haven't seen this before. And I'll do my whole cheese sandwich thing. But if I had, let's say I want to make a cheese sandwich. That's cheese, by the way, Swiss cheese. And this is bread. Again, not very good artistry here. Again, you know what a cheese sandwich looks like. I'm not going to try and draw it. But it's going to be 2 slices of bread with a slice of cheese in between, and that's what that's supposed to represent. So if you had, say, 3 slices of cheese and 6 slices of bread, I think you'd be fine with saying you could have three sandwiches. But if you had, let's say, 3 slices of cheese and then 10 slices of bread, how many sandwiches do you think you could make? Anybody want to answer that? You had 3 slices of cheese and 10 slices of bread. How many sandwiches could you make? Sorry?
If you only had 3 cheeses, you would only have 3 sandwiches.
That's right. Okay, here's a more advanced question. How many slices of bread would you have left over? How many slices of bread would you have left over?
4.
4 is right. So what you'd use is you'd have 3, you'd have 6. Now the way you get this is 6 divided by 2, which is 3. So that's where that mole ratio thing comes into play. That's why we're dividing it by that. So it's 3 divided by 1, which is 3, and 6 divided by 2, which is 3. So that's why we're dividing by the number of moles in the reaction. It's the same effect as what we're doing with making a cheese sandwich. And that's all I really want to point out here. Does anybody have any questions? All right.
Could you undo to go back to the problem you just did?
I don't think so. I don't think I have that kind of power, Ashley. What did you want to know? I can't go back that far. That many undos on this.
The only thing I've seemed to be having, and it's only sometimes, is proper labeling. So like on the homework, it's a little, I guess, easier because you have them there. On the test, you have to fill it out manually.
Can I hold off on this until we get to the next part where we're looking at the practice quiz?
Yeah, for sure.
Let's do that, because I'm going to go through an example on the practice quiz as well.
Okay.
And that will, I think that'll help with your question, probably more than what this would anyway. So let's take a look at that. Yeah, the practice quiz is also like what you'll do on the test as well. So it's this kind of thing you're talking about, right, Ashley? The labeling. So I'm just going to do I'll do a couple of these, but then I'll mainly focus on the percent yield and the limiting reagent question when we get to it. So for this one here, again, we're going to be using this modified flowchart. We're starting out with 165 grams of HBr. And what we're looking for here is Grams of H2 is what we're looking
Grams
for.
of H2.
Yeah. So we know that we'll need that number of steps. We can actually see that there as well. But we know grams of H2 is what we want at the end. Whoops, not grams of H2, grams of H2. So we'll have grams of H2 here as well at the end. So we know that following above here, we've got grams of HBr. That'll be moles of HBr that goes here. And moles of H2 will go here. See, it just follows along. Grams of HBr, moles of HBr, moles of H2, grams of H2. And that's how it's going to be across the top here. And then we just put these down the bottom. So to help with the labeling, I really recommend writing this down on paper so that you are very clear about what goes where. And then we can put our relationships in. It's 1 mole of HBr is equal to 80.91 grams. And then the relationship here is going to be 1 mole of H2, and it looks like 2 moles of HBr. And then the grams of H2, that's going to be, I think it's 2.02 and 1 mole. And then we come up with our answer over here. Now to put this into your calculator, and this will go for the on-lock calculator as well. Here's how I would do it. I do 165, I do times 2.02. So I multiply everything on the top and I just divide by everything that's on the bottom. And that works. That's how I put it in my calculator. Multiply everything across the top, divide everything that's on the bottom. And I end up here with 2.06 grams of H2. Number of sig figs, this is going to be 3 sig figs over here. So I end up with 3 sig figs in my final answer as well. Okay, any questions about that? Any questions? Well, pretty much all these other ones are very similarly done to that, except when we get to the percent yield, which I want to focus on here because that's one that people often have trouble with. So what are we looking for here? Well, we're looking for the percent yield of HBr if 85.00 grams of HBr was formed from 30 grams of H2. So we're looking for the theoretical yield. And I don't give you a great number of clues as to what to start with or what to go towards because I want you to come up with that on your own. So the clue I can give you here is the same clue as what I gave you when we were going through the assignment. And that is that we're going to always be starting out with a reactant and going to a product. And if you remember what I had said about reactants and products, what we start with is the reactant, what we finish with is the product. And here we're looking for the percent yield of HBr. It's always the percent yield of a product that we're looking for. And that means we have to start off with the reactant. The reactant here is H2, so that's what we're going to start with, 30 grams of H2. And we're looking for the grams of HBr. So I'll stop there for a second. Once you get to that point, that's half the battle won. Knowing what you're starting with and what you have to finish with. Does anybody have any questions? You're all fine with that, huh? All right. So then we do the same thing as with what we've been doing. And we're looking for grams of HBr at the end. So now that goes here. What goes here? Well, moles of H2 goes here. Moles of HBr goes over here. Then the grams of H2 cancels. The moles of H2 cancel. and the moles of HBr cancel. We put in our relationships. 1 mole is 2.202 grams of H2. The relationship between HBr and H2, again, is 2 moles of HBr, 1 mole of H2. And then the grams of HBr, 80.91 is 1 mole. And that will allow us to come up with the grams of HBr here, which will represent the theoretical yield. And again, I will do 30 times 80.91, and then times 2. That's multiplying everything that's on the top there, and then divide by whatever's on the bottom, and that's 2.02. And I get there 2403 grams, but if we convert that to significant figures, it'll be 2400 grams of HBr. That only has 2 sig figs. That's what we started with. Any questions? So that's how many grams of HBr we should have gotten. So in order to figure out the percent yield of that, the percent yield is going to equal our actual divided by the theoretical, multiplied by 100%. The actual is 85.00 grams. We're given that in the problem. Divided by what we actually should have gotten, the theoretical yield, multiplied by 100%. And that should be, let's see, 85 divided by 2400. And it should be 3.5%. And that would be the percent yield. Does anybody have any questions about number 5 there? Any questions? All right. So actually, I think this will help you with the labeling on this part. I think that's what you're going to be asking about, right? So what we've got here is 45.0 litres of H2, and we've got 60.0 litres of O2. You'll notice that both of those are reactants. So think of the cheese sandwich. It was bread and cheese, same deal. And that would be the cheese sandwich over here. So that would be the product. But here we're just dealing with 2 reactants. Follow the same pattern. We're going to do moles first. So 45.0 litres of H2. We want to figure out how many moles we have of that. So it'd be moles of H2 over litres of H2 to make that cancel. 1 mole, 22.414. And then we need to divide that by the number of moles, which in this case is 1. And we get that from the coefficients here. It's be 1 mole of H2. And that would be, let's see, it's a mole ratio, 45 divided by 22.414, which would be 2.01. And that doesn't have a unit on it. And the other one, 60.0 litres of O2. Again, we figure out the number of moles we have to be moles of O2 over litres of O2 to cancel 1 mole, 22.414 litres. And then times 1 over the number of moles in the reaction equation, which is 1 mole O2. So 60 divided by 22.414, 2.68. And again, no units on that. The limiting reagent here is the smaller one, which is going to be the H2. When we look at the mole ratios there. All right, actually, specifically, what issues were you having with the labeling when you put them in here?
Sometimes I just get a little confused on like what goes where. I understand, you know, more or less how to get the number of moles because that comes from the problem. But sometimes it's not like extremely obvious what the moles are. And then that can, like you get a little bit of help because, you know, obviously they have to cancel.
Well, I think maybe what could help is if you numbered them, you did it on paper and then numbered them, makes this 1, 2, 3, 4, 5, and then 6, 7, 8, 9, 10, 11. So that way you shouldn't get confused if you do that. So then it just matches what you've got up here. That's how I would do it, because I understand it can get confusing if you get mixed up with what number is going with what number. Okay, I think we lost Ashley. Okay, does anybody have any other questions about this? Okay. So that's what the practice quiz and then also what the credit quiz is going to look like as well. Let's go take a look at what you're going to see on the test here. Just looking, hang on, let's go back to test 3 here. Okay. Practice test 3. Let's look at the kinds of questions you can expect to see that relate to Module 9. So,
Professor Richard,
sorry, yeah.
I have a question, just I not forget. How you can make the zoom for the periodic table you have in the test?
Could you repeat that, please?
How you can make the zoom for the periodic table you have in the test?
Make the what? Zoom? Oh, okay. Yeah, control. What kind of computer do you have, Anna? A PC or a Mac?
I have Mac.
You have a Mac. Okay, so you want to use Command plus.
Oh, okay, cool. Okay, yeah, because I have trouble in the test, but no. Thank you so much. Appreciate it.
Command plus to make it large, and then Command minus to make it smaller.
Oh, okay, cool. Thank
you. And if for anybody who's watching this who's on a PC, it's Control, CTRL plus and CTRL minus.
Oh, okay, good. Thank you so much.
I think there's also in the settings here, view, I think, yeah. You can look at the zoom in, zoom out. See that? On Chrome?
Yes, but when you are in the test,
you might not. Yeah.
You don't have any function.
Yeah, no,
Even though it's so, if you try to do something with the mouse, they pause the test. So I say, oh, okay.
Yeah, I think the zoom works though.
Okay.
Yeah, under on a lock. I think it does. I think I've tried it before. I think it's okay.
Okay, thank you.
All right. Okay. So for something like this, number 9, it's very similar to what we were just looking at in the practice quiz. So I don't feel like I need to go over that again because it's the same kind of deal. We again put in the numbers and match up whatever goes here with whatever goes into these boxes. It's the same kind of deal here on the limiting reagent problem. That's what we were just looking at. And then the theoretical yield, just the same thing, and we get 2 of those problems as well. So it's very similar to what we just dealt with in the practice quiz. I mean, really no different, same kinds of problems. So for those specific problems, does anybody have any questions about problems 9 through, well, let's see, what would it be, 9 through 12, I guess, on the test? Does anybody have any questions? I mean, I'm happy to go over whatever anybody wants to go over. It's very similar to what you did. Pietro, do you have any questions? You just popped in.
Oh shit. Sorry.
You all right?
Yeah, I'm sorry. I'm just came in through my phone.
No, okay. Do you have any questions about the test, or especially with relation to Module 9?
My biggest concern or my biggest questions are really with Module 8.
Oh, okay.
I can review it earlier. I can see the recording for it later.
Okay. Well, we can always talk about it after I get off the line here as well. So anybody who wants to hang around can hang around. So if you want to hang out, Pietro, we can do that. So just hang about for a sec.
Okay.
All right, Anna, Kayla, do you have any questions about what we've gone over here, especially with relation to Module 9 and the questions you're going to see on the test?
No, Professor. Thank you so much for the time.
Yeah, no worries. No worries. All right, well, we'll end it here then. I'm going to stop the recording here at this point. Pietro, I'll answer your questions. If anybody wants to hang around and listen in, they're more than welcome to. Still want to keep on end the